Hello students, welcome to lecture 29 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on guided mode resonance. So here is the lecture outline. We'll give a quick introduction to guided mode resonance. We'll go through the definition, the basic concepts and theory, some of the polarization properties of the guided mode resonance, and then we will see the filter design based on guided mode resonance, the filter spectral response and resonance regime of GMR, and then we will provide a summary of this particular topic. So, the first question comes to mind is, what is guided mode resonance? So, we have seen resonance phenomena in photonics, which actually allow for strong localization of electromagnetic waves, and that has got numerous applications, something like narrowband filtering, chemical and biological sensing, lasing, harmonic generation, Raman scattering, photovoltaics, etc. Now, the important parameters that describe a resonance feature are its intensity and the spectral line width. That will actually decide the Q factor, the quality factor of the resonance. In most practical applications, resonances with strong intensity and narrow line width are desirable. As you can understand, high Q resonances are always desirable in most practical applications. There are applications where you actually look for broadband absorption or broadband resonance. Those cases will come in the subsequent lectures. Today we are looking for very narrow line width filters. Okay. So, high resonance intensity, what are the benefits? That can give you better signal to noise ratio, and when you have narrow line width, that actually gives you very strong field confinement. So, you are actually focusing your beam at a very narrow spot. So, this is what is the thing you can relate to narrow line width. So, it can give you larger field confinement. However, most of the resonances are constrained by a kind of trade-off between these two important parameters, resonance intensity and line width, and this limits the possibility of independent tailoring of the resonant features at will. So, you are not able to kind of tune intensity and line width independently based on your requirement. So, that luxury is not there. Now, when you think of guided mode resonance, this is where the guided mode resonance becomes very important. So, it can provide a tailorable resonance intensity with narrow line width through geometrical design and selection of materials. So, this kind of filters, the filters designed based on guided mode resonance can give you very high quality factor. So, due to this versatile nature of GMRs, they are found in a wide range of applications. One application we can see here is that high Q filter. So, this is how typically a GMR will look like. So, it is a guided mode resonance, there is a grating and then there is a waveguide below this. So, as you can see, there is light incident, some part is getting reflected and the remaining is getting transmitted. So, the refractive index here, this is air, so you can take refractive index to be 1, this is silica, so it is 1.4. We are considering the periodicity, the lattice period to be 6.91, that is the grating period. Okay. You can think of high low, and these are made of germanium and selenium. So, that is n equal 4 and 2.64, and when you actually look into the grating thickness, this is particular thickness of the grating, that is 3.8 micrometer, and the fill factor of the high material is 0.42. So, 42% of the grating period is basically germanium, the remaining is Se. Okay. So, with that, when you see the diffraction efficiency, you will see that over the wavelength, if this is the wavelength thing, so this actually gives the spectrum. So, the blue one tells you the transmission peak, it is a very narrow peak as you can see, okay, and it is giving also a reflection dip. So, that particular wavelength, only one particular wavelength is able to escape and remaining all are reflected. You can also look into the electric field profile at the peak wavelength of T0, and that corresponds to the TE polarization state. And what is this dashed line? That is basically the effective homogeneous layer. So, here you see you do not actually see any kind of resonance. So, the resonance comes from the grating, and the grating does something which, because of which you are able to only allow one particular wavelength to pass through it, remaining all are getting reflected. So, there is something very interesting about this particular phenomena. So, as you see that GMR devices primarily consist of a diffractive grating, and then you have a in plane waveguide. The grating will diffract the incident light, and some diffracted wave will basically couple to the waveguide, and it propagates as the guided mode. And this guided mode is designed to be leaky, and it leaks out when it interferes with the free space propagating electromagnetic wave, and that gives that resonance GMR. Okay. So, through the selection of material, grating design, dielectric layer thickness, angle of incidence, the GMR can provide a wide range of spectral features. So, you can actually tune the transmission or resonance peak or deep, as you can see here, depending on all these parameters, which are very easily tunable. So, that makes this GMR filters very interesting. So, there are other names of this particular device. It is also called resonant waveguide gratings, RWG, or we have already seen this name GMR grating, or you can also call them waveguide mode resonant gratings. Okay. So, these RWGs, as you can see, they are basically dielectric structures where the resonant diffractive element, they actually benefit from the leaky guided modes. Okay. And they can be tuned from UV to microwave and other frequencies also, okay, for different configuration. Mainly they are used in this particular range, and they can also be tuned to optical and infrared. Okay. So, a resonant waveguide grating can be defined as a thin waveguiding film in optical contact, okay, or it is merged with a grating, as you can see here. Okay. So, this particular one actually shows the grating, and then there is this waveguide below it. Okay. So, this particular figure shows a 4-port configuration. So, 1, 2, 3, 4, there are 4 ports, and the white arrows are basically the inputs, okay, and the blue ones are basically the outputs. Okay. Light is considered to be incident from the free space, which is coupled into a waveguide mode, and then that can outcouple resonantly in a specular reflection or transmission, and that is how it works. And here the substrate and superstrate, they are not shown, but they actually act as a cladding. So, when you think of this waveguiding film, okay, it operates usually by having a higher refractive index than the surrounding media, because that is how waveguiding will take place. Waveguiding typically happens based on your total internal reflection, for which the core, this will be the core in that case, waveguide core has to have a higher refractive index than the cladding. The thin film supports a discrete number of guided modes because of its thin dimension. So, the finite number of modes are allowed, and the waveguide modes can be limited to the fundamental mode, that is the 0th order mode, in case this is very thin, or it can actually go up to few modes if they are bit slightly thicker, and for TE and TM polarization you can have different mode indices. Now, depending on the wavelength, this leads to a very high reflection or transmission, giving rise to 0th order reflection, as you can see here. Okay. So, this is how the grating is made on top of a thin waveguide, and you see this is the incident plane wave. Some part is getting reflected, some is getting diffracted, and when this diffracted mode couples with the leaky mode, okay, it actually, so this is how it travels, okay, and it leaks out as well. So, this is how you actually get the transmission. Okay. So, in this particular example, it has been designed to have a reflection peak and a transmission deep. So, you can actually design the filters or the guided mode resonance filters like that. So, those efficient resonances that you have seen here can be as narrow as 0.1 nanometer line width, and they are very sensitive to the incident angle and the wavelength. And you can see a typical angular to spectral line width ratio is like 0.1 degree nanometer inverse. So, you can actually see they are very sharp, so they can give rise to very high Q resonance, and they are also tunable. Now, depending on the length and the phase delay that is accumulated during the propagation in the waveguide, the destructive interference can occur either in reflection or in transmission. Now, this is why in the previous case we saw a transmission peak, in this case we saw a transmission dip. So, you can actually, so the modes that are coming, the waves that are coming out, if the destructivity interfere, they will cancel that particular transmission at that particular wavelength. If they constructively interfere, they will get a peak. So, you can actually design this particular phase delay, and that is accumulated along the propagation of the waveguide. So, the length of this device also plays a important role. Now, for a given polarization and wavelength, an RWG can support various guided modes, as you can understand, having different mode index and therefore transverse polarization, different transverse propagation speed and momentum. So, light can be coupled to the waveguide modes by different grating orders. So, diffraction grating, if you remember, not only the 0th order, there will be +1, +1 -1, +2 -2, +3 -3 and so on. So, all the diffraction orders are possible. So, particular which angle that actually meet that is more than the critical angle at this interface, that will be totally internally reflected, and that will continue to propagate in this waveguide, right, and some part of it will leak out, and that is how the leaky waves are also coming. So, in this particular case, you can see that some of this guided wave is diffracted out of the waveguide while propagating, coupling back to the radiation, and interferes with the non-coupled reflected lights. So, here the reflected ones are basically, okay, the reflected ones, this should be blue, the reflected ones should be, okay, there is a mistake here. So, the reflected ones are basically magenta and transmitted ones are blue, okay. So, yeah, this should be corrected. So, this is how it works, okay. So, here you can actually see this light yellowish kind of wave propagation inside. So, when a complete destructive interference happens in the transmission, that happens at a specific angle and a specific wavelength, you can actually get a narrowband reflection. So, that is how you can actually get this particular feature, as you have seen here. So, it is clear that this RWGs or GMRs are very good at filtering, okay, and for especially for collimated light, they are very good filters, and they have extremely efficient diffraction elements they can be designed to be, okay, and the structures usually consist of all dielectric materials. So, they are highly transparent, and they can be used either in transmission or reflection mode. There is nothing absorbing here, there is no metallic component. So, these structures do not suffer from thermal heating, and they can be used for very high optical power applications such as mirrors or other diffractive elements. So, these are safe to use, they will not heat up. Now, depending on the geometry, there are different types of RWGs, okay. So, each ridge and groove corrugating the waveguide layer that you see, this one, this is how you are corrugating the waveguide layer, okay. You can actually design different kind of RWGs. So, this one, as you see, this is a single sided rectangular corrugation of the waveguiding layer, but this one is a double sided corrugation, okay. This one is a waveguiding layer corrugated to its full thickness. So, it is basically, you have just etched the entire thing, okay, and this is actually giving you discrete ribbon kind of structure. and this is the same thing, but you are having this ribbons on top of a waveguiding layer. This is a single sided sinusoidal corrugation of the waveguiding layer, whereas this one is a double sided sinusoidal corrugation. So, these are different kind of corrugations that you can make, okay, and they actually decide the pattern of your quasi guided or leaky modes, and also tell what kind of mode can propagate. Okay. So, RWGs can therefore be considered as temporal or spatial optical integrators, as well as they can be used to enhance the local electromagnetic field, as example for sensing or nonlinear optics applications. Now, let us have a look at the basic concepts of GMR. Okay. So, this is a grating structure and this is the waveguide that you have seen. Now, in most elementary structure, in this case is a planar unslanted grating, okay, in a asymmetric waveguide geometry. Why we are calling asymmetric? Because epsilon 1 and epsilon 3 are not same here, that we take them as different. And the relative permittivity or the dielectric constant of this region 2 can be spatially modulated like this. So, this is x direction, this is z. So, epsilon x can be varied like this. Epsilon g is basically the average relative permittivity, and delta epsilon is the modulation amplitude, and it is having a cosine variation, where k is basically 2 pi by lambda, while lambda, capital lambda, is the grating period. Now, we understand that the waveguide grating, okay, this is the waveguide grating. So, it should have a permittivity which is larger than both epsilon 1 and epsilon 3. Okay. So, this is where the waveguide grating is. Okay. So, this is also called as guided mode resonance filter or GMRF. Now, for T polarization, you can consider the electric field vectors to be normal to the plane of incidence in this figure. Okay. The coupled mode equations which govern the wave propagation in this waveguide grating can be written in this form. I will not go into the details of this, but I will just highlight the few important factors, that is, this S cap is basically the amplitude of the inhomogeneous plane wave of the ith space harmonic. So, you have got this I index, k is basically the free space wavelength, and theta is the internal angle of reflection, and that is this one. Okay. So, you start with the coupled mode equations, and when you put delta phi equals 0 in this equation, okay, you actually make this to be an unmodulated dielectric waveguide. It simply becomes a normal waveguide. So, in that case, the equation also simplifies, and it looks like a normal wave equation of this form, where beta is the propagation constant. Now, a guided wave can be excited if the average or if the effective waveguide index of refraction n, that is given by beta by k, is in this range. So, it has to be, the modulus of n should be lower than square root of epsilon g, but it has to be greater than or equal to the maximum of the refractive index of this or this, whichever is maximum. So, this is how you can ensure that the mode will be propagating guided. Okay. So, this is a very common kind of requirement that comes from the waveguides that you can study in any other course. Okay. But one important thing is that when you put this delta epsilon to be 0 in that equation, and when you compare that with the equation 2 that we have seen here, okay, you can find out that beta can be written as this. Okay. So, that is basically the effective propagation constant in the waveguide grating, and this also corresponds to a effective refractive index, but it corresponds to the ith mode. Okay. So, Ni can be written as beta I over k. Now, the propagation constant beta I of the waveguiding in the limit that delta epsilon is 0 or tending to 0, okay, is thus given in the terms of the basic parameters, something like basic waveguiding grating parameter, that is capital lambda, epsilon g, theta, lambda, I, and all these things. So, this is how you can actually see these two equations, and you can put the same arguments here also for the TM case, and you will see that these equations are valid, these conditions are valid for both TE and TM polarization. Okay. So, here let us refer to the eigenmode equations of this unmodulated slab waveguide. Okay. So, this will become a slab waveguide when delta epsilon tends to 0, as you can understand. The corresponding eigenvalue equation of the modulated waveguide can be written as this. So, you can actually find out that 10 delta 10 kappa I d will be given by this one. So, kappa I is related to the propagation constant in the different regions. Okay. So, these are again all coming from the waveguide theory. So, we will just have a quick look, we will not go into very much details of this. I am just showing you the formula here that will give you some idea that how this the GMR effect has come. So, for TM polarization, the eigenvalue equation looks like this. So, the previous one was for T, this one is for TM. So, in the limit of delta epsilon tending to 0, okay. So, the equation that you have seen for T or TM and the range that is equation 3, this one, they are all holding good. So, they all govern the mode coupling. So, it all tell you that which all modes are possible. Okay. This is that equation 3, and this also governs the resonant behavior of this waveguide grating filter with the modified propagation constant beta I. Okay. So, here in this case this will contain the grating parameters explicitly. What is D? You remember, D is basically the thickness of this waveguide grating. So, these are the conditions that you have seen, okay, and for any parameter varied, in fact, the resonance free parametric range in the limit of epsilon tending to 0 can be found from these two equations. So, these are the eigenmode equations that tell you the modes which are allowed to propagate in this particular grating, and this you can find because all these coefficients gamma I, delta I and kappa I, they depend on epsilon, g, theta, lambda. This is the wavelength of light, this is the grating period, and this is the index. Okay. So, the resonance free region especially represents the separation between the two modes. Makes sense? So, every resonant mode is there, and there is also a region between those where different modes can propagate in a equivalent unmodulated slab waveguide that corresponds to the waveguide grating. So, whenever there is a grating, there are some specific modes. So, in between there will be some resonance free region. So, we will also look into those, how to identify those particular region. Now, if the ith diffracted wave corresponds to the guided mode, then the resonance free range in the thickness for both T and TM polarization can be given as delta D, which is pi over kappa I, and you can write this as, expand this in this particular form. So, let us take one example. So, if you are looking at the T eigenvalue equation, so the T eigenvalue equation was written as this, okay, and when you solve for lambda, that gives a free spectral range that can be written as delta lambda FSR nu, and that is basically the resonance at nu plus 1 minus the resonance wavelength at nu. So, nu is basically your 0, 1, 2 and so on. These are the integers which are used for leveling the waveguide modes. Now, since the eigenvalue expressions for T and TM modes are different and the resonance occur at different parametric locations, okay. So, that is easily understood that the eigenvalue equations for T and TM modes are different. So, the resonance for T and TM mode will occur at different parametric location. Okay. So, these are the two equations for your quick reference. Now, you can consider these as parameters, okay, and that will allow you to calculate. These are like some parameters that you can take, and you can calculate what will be the positions of the TE and TM resonance modes. Now, to quantify the TE TM polarization separation of the filters, you can apply these equations to produce this particular graph. So, this is how you are plotting the TE0 and this TM0. Okay, this is TE1, TM1, and this is TE2 and TM2. So, what are these? These are basically showing you the TE TM polarization separation, and the normalized, all these are normalized to the, so this is basically the grating thickness normalized by its period, this is the lambda normalized to the grating period. So, these are normalized one. This also tells you about the separation between the modes, okay, and it also tells you the resonance free regions. So, these are the regions which are free of resonances. So, for a given normalized filter thickness, okay, d lambda, the normalized wavelength separation between T and TM mode you can find from here. Okay. So, these are basically, so for a particular value you can find out what is the lambda separation for 0th order TM mode and 0th order TE mode. You can use this graph and find it out. So, if you assume that D equals say 1000 nanometer, okay, and you can see that the fundamental that mode, that is nu equals 0, and if you consider the separation between the T0 and TM0, you will find that the resonances are separated by 24 nanometer. So, that you can find from this particular graph. Okay. Other kind of separations, like what is the separation between T0 and like this particular, when you take this value you can actually have T1 mode as well as T0 mode, you can actually find out what is the lambda corresponding to these two resonances. So, this particular figure is very important because it gives you all these resonance positions, and also it tells you about the resonance free regions. Okay. Now, as we have considered normal incidence in this example, so here what are the parameters? If you see the parameters, this will be the parameters considered. Okay. So, we are considering normal incidence and other parameters are also given. So, the inequality actually boils down to this. So, this is the condition. When you put epsilon 1 and epsilon 2 and other parameters, you will see this is the condition that will actually give the normalized wavelength range that you see. So, this particular range 1.47 to 1.73. So, this is the range that you have plotted here. So, this has basically come from this one. Okay. So, this actually tells you, so you have actually put I equals plus minus 1 in this equation, okay, and you have obtained epsilon 1, epsilon 3 are the values that you have shown there. So, once you put that, you will get this particular range. So, this is why this particular range is considered, because in this configuration or the material choice, this will be the normalized wavelength that you have to consider. Now, the figure also additionally can be used to find out the resonance free region, as I told you. So, you can actually see these regions, okay, in filter wavelength and thickness, in both parameter which region is resonance free you can find out. So, you can actually take d by lambda equals constant like this and obtain those region where resonance is not there, or you can consider the thickness and see whichever portion has no resonance. So, the analytical expression you can obtain for resonance free range. So, when you calculate, so you will see the delta d, that is the in thickness, what is that thickness where there is no resonance, you can obtain it like this. I am not going to the details of these equations, there are complicated equations, you can obtain them from this particular paper, but this actually tells you how this separations are basically obtained. And when you combine this inequality of this equation and this one, you will actually get this particular equation, because you know the relationship between beta by k is basically your n. So, you can put this guy here and you will get this particular expression. So, here you can also see that if you want to make epsilon square root of epsilon 1, that is n1 sin theta 1 equals the refractive index of this one, that is square root of epsilon g sin theta. Okay. So, that way you will be able to make a range which are the allowed angles for your particular device. So, with that you can identify the resonance regime. Okay. So, this expression allows you to define the parametric regime where the guided mode resonance actually occurs. So, this is particularly a plot that shows those resonance regime. Okay. So, on the x axis you have the normalized wavelength, and on the y axis you have angle theta. Okay. So, this actually gives you the selected values of the average permittivities with the diffraction order I as a parameter. So, here you see this is for I equals plus 1, this is I equals minus 1, this is I equals plus 2, this is I equals minus 2. Okay. And again the parameters that we have considered here is epsilon 1 is 1, epsilon g is 3 and epsilon 3 is 2.161. So, the solid curves that you see here on the left side of the inequality. Okay. So, here the left side of the inequality is actually coming from this solid line. Okay. And the right side is shown by this dashed line that is coming from this one. So, the right side inequality gives you this one for a particular I, okay, and the left side inequality gives you this solid line, okay, for that particular I. And the shaded region between the two lines are basically those parameter values for which resonance can takes place. So, this can be called as resonance regime, okay, and these are the boundaries for I equals 1. Right. So, the solid boundaries correspond to the diffracted order I at the gazing angle, okay, at which the classic Rayleigh anomaly is associated. So, we will see what is that Rayleigh anomaly in the next slides. So, here one important thing is to note that at the intersection of the two solid curves, a double Rayleigh anomaly takes place. Okay, something like this. Now, when you say about Rayleigh anomaly, this is nothing but a anomalous or abnormal behavior of light that is being reflected from a periodically corrugated surface or diffraction grating that was observed in the form of rapid variation of intensity of the diffraction orders as a function of the wavelength. So, it happens like this, a sharp intensity variation and related exclusively to the emergence of diffracted beams when the incident beam is at glazing angle, and you will also get beams which are parallel to the surface of the grating. So, Rayleigh was the first to represent this particular effect, and he was able to explain this. So, that is why the anomaly is named after him. It was pointed out that the anomaly in reflection occurs at wavelengths for which one of the diffracted order becomes parallel to the main plane of the grating, like this, okay, and then eventually it will vanish at greater wavelengths, because after that you cannot actually like the reflected one cannot go inside. So, that has to vanish. Okay. So, this changes the power distribution among the remaining diffraction orders, including the specular reflection or the zeroth order reflection, right. So, if one mode is not allowed or one particular order is vanishing, so the power has to be distributed among the remaining. So, that is how the anomaly disturbs the system. Now, another cause of the anomalous behavior takes into account the possible existence of leaky modes located at the surface. So, which are coupled to the incident wave, such as in the case of surface plasmon polaritons. So, there also you can see in the case of grating, it is mainly for those diffracted beam orders which are basically parallel to the grating. Now, in the case of the flat surface, the waveguides of such surface waves are greater than the incident waves, so that they do not interact. But when you look for periodic structures, the wave vectors of the grating come into the play. So, because of that, the grating or because of that the coupling becomes possible, and as a result at certain frequency the incident wave will generate the leaky surface waves, and in that case the reflected power will decrease. So, this effect becomes resonant, and because of that the reflection curve will get a narrow dip, very narrow dip, and that will also give you a transmission maximum. So, for the light diffraction at the periodic structure which has got a grating number of g, okay, g can be written as 2 pi by the lattice period, okay, you can say that Rayleigh anomaly will occur if kx plus n times g will be equal to the incident wave vector. So, if this matches, so n is basically 1, 2, 3, this is happening because of the grating. When there is a match, okay, so a Rayleigh anomaly will take place, the wave will leak in, okay, and you will get a reflection dip. So, here k is the wave vector or wave number of the incident light, and kx basically is the component of the component that is parallel to the grating plane of the wave vector, right. Okay. So, the two symmetric double Rayleigh anomalies can be seen here when the incident angle is 0 degree. You can see it for I plus minus 1, there is a degeneracy, the other one is for I plus minus 2. So, these are basically symmetric double Rayleigh anomalies. There is also one asymmetric double Rayleigh anomaly that happens at theta equals 30 degree when I equals plus 2 and I equals minus 1. Okay. Now, during the interval designated as this resonance regime, the order I can actually correspond to the guided mode. So, you can say this is the first order, second order, and so on, and this is the equation that you have already seen. So, this theta is the incident angle, and this limit tells you that which all modes, including the order of the mode, that can be allowed to propagate. Now, if you look into the dashed curve, okay, with the increasing wavelength, now beyond the dashed curve, that is we are looking for this one, the dashed curves, okay, the order I is neither propagating nor it is possible to, beyond this it is not able to propagate or it is not even guided. So, in order to actually strike a resonance with this particular regime, the eigenvalue equations need to be satisfied. So, these are the equations that need to be satisfied to fall within this particular regime, right. So, these are the supported modes which basically can propagate and leak out and give you that resonance. Now, their solutions fall within the resonance regime with the location additionally dependent on the thickness of the filter, that is the parameter D. So, here you can see at 0 degree the resonance of plus minus 1 is indistinguishable because they are overlapping here, and at non-zero theta prime, that is at non-zero degeneracy. So, you can put plus minus 1 and you can actually see that they actually do not have the degeneracy anymore. And the solid curve that you see here, that is labeled as lambda r over capital lambda, this indicates the last propagating higher order diffracted mode, that is here in this case it is I equals plus 1, okay, and it gets cut off at grazing angle, okay, as the wavelength is permitted to increase. So, as you keep on increasing, it actually does not increase further, it will actually get cut off here. So, this r is basically the Rayleigh wavelength. So, you can actually call this as the Rayleigh wavelength, okay, and when lambda is greater than lambda r, okay, you can say only 0th order wave can propagate. Okay. So, in this regime only the 0th order mode will be propagating, not the higher order modes. So, the diagram such as this figure are also useful in visualizing the resonance properties of diffraction gratings. Now, let us look at the effect of modulation amplitude. Okay. So, this particular figure calculates an example of the spectral behavior of the symmetric high symmetric filter or symmetric waveguide. Symmetric means epsilon 1 is considered to be same as epsilon 3. Okay. And it has high spatial frequency. So, lambda is considered to be greater than the grating period. Okay. And what are the parameters? So, epsilon 1, epsilon 3 to be taken as 2.5, epsilon g is 3, this normal incidence, these are the parameters. We have considered the center free space wavelength to be 1.669 and the line width we got is 0.01 nanometer, and this D10 these are basically the diffraction efficiencies. Okay. So, 10 is reflected, 30 is the transmitted one. So, you can only see that the 0 forward and backward diffracted waves propagate, and in this case all other modes are basically cut off, right. And the diffraction efficiency represents the intensity of the various diffracted wave. So, here you can see that this is 30, the transmitted one is getting a dip and the reflection one 10 is getting a peak. Okay. And there is 100% energy exchange between these two modes and the smooth lines can be obtained. And what is the good thing about this kind of symmetric filter? The symmetric waveguide grating filter, they also produce very symmetric spectral response. So, you have 0 nulls on both sides of the peak, and that is a perfectly symmetrical filter, which is usually not the case with any other resonant kind of structure. And if you see the transmission, you get a very beautiful notch filter. Okay. And if you are allowing the higher order waves to propagate, you will see that pure nulls may not be obtained. So, one of these legs will be kind of asymmetrical and it will be different. So, if you look into asymmetrical filter where you have epsilon 1 not equal to epsilon 3 and these are the parameters. So, in that case surely your spectral response is not symmetrical and you do not have null on both sides, perfect null on both sides. Let us also look into the effect of amplitude modulation. Okay. So, here it shows the normalized filter line width as a function of the modulation amplitude of the waveguide grating. So, these are all kind of normalized. So, delta epsilon is the modulation index and delta lambda is basically the line width, and if you take these are the parameters. So, this is an asymmetric parameter, and you can see that if you consider grating period to be 1 micrometer, the line width that you calculate falls in the range of 20 femtometer to 200 picometer. So, that is basically the range. So, you can understand how narrow these resonance filters are, and they are very high quality resonance, and this is a graph that will tell you that for what kind of modulation you should have what kind of line width. You can also think about the mode confinement from this particular graph. It allows you to see the spectral line width can also be controlled by the degree of confinement of the mode in an associated unmodulated waveguide. So, if you do not have modulation and you can think of an effective unmodulated waveguide. So, this particular figure shows the numerically calculated plot of normalized line width. So, here you are taking a symmetric case, okay, but you are considering the difference in the refractive index to be your x axis and you are varying the line width. So, here you will see that you are varying the parameters from 1 to 2.95, right. This is the epsilon 1 that you are varying, and this is how you actually get this variation. Okay. So, strongly confined states, something like delta n will be tending to 0, exhibit the largest line width. You can also use this for electro optic switching in some applications, something like this particular filter illustrates the resonance line under the variation of the average grating permittivity of an asymmetric filter or asymmetric waveguide grating structure. So, here you can see there are many other modes which are getting diffracted. So, here in this particular example the break grating is satisfied, but this is not a condition requirement for the resonance to occur. So, the break grating condition lambda over capital lambda equals 2 sin theta is satisfied here, and these are the parameters that we considered, and you see that 1 0 1 1 3 0 3 1 these modes are also present. Okay, and that is why you are not seeing perfect null in this resonance. The point is that here the resonance can also occur under break condition, and with non-zero diffracted wave also propagating, as you can see here in this inset, pure nulls are not obtained next to the resonance, and a variation in the average relative permittivity can then introduce a resonance. So, in that case a electro-optic effect can be used to switch energy from the transmitted to the reflected, because you can change slightly the effective relative permittivity of this grating, and that can introduce the resonance or it can move out the resonance. So, you can actually use a electro-optic effect for getting this resonance or not. Okay. This particular figure shows the calculated TE filter reflectivity as a function of wavelength with different incident angles. So, you have got theta equals 0, plus 10, minus 10, plus 20, minus 20, plus 30, minus 30 and so on. So, the peak efficiencies, they are all dependent on the incident angle as well. So, here are the parameters which are used for calculating this, and for this particular case you have also obtained what are the resonance regime as we have seen. So, here you can actually see that we have calculated for I equals plus 1 and minus 1. Okay. And there is a large peak corresponds to I equals minus 1, with smaller peaks happening at I equals plus 2. Okay, because there is a case here corresponding to 30. Okay, so here you can see that this is the case for theta prime equals 30 degree, which corresponds to your plus 2. Okay. The large peak at theta prime equals 30 degree corresponds to I equals minus 1. So, this one, with a smaller peak caused by the wave with I equals plus 2. So, I equals plus 2 gives this particular smaller width. Okay. So, this is basically seen from this one. So, the same results can also be demonstrated for that other polarization case, TM polarization case. So, in this case you can see the resonances are even more narrower. Okay. And with that we will conclude what we understood in the GMR. So, RWG or GMR, basically they use the periodicity of a grating to couple light into a thin waveguide. They have been therefore used very extensively as waveguide couplers for optical communication and signal processing for both in-coupling and out-coupling of thin waveguide modes with strong wavelength, polarization and angular dependence. Their in-coupled quasi-guided mode can interfere dramatically with the incident illumination depending on the phase delay that is accumulated in the in-coupling of the waveguide, which can create anomalous reflection or transmission features, creating unique zeroth order properties. So, you can actually get those very sharp reflection or transmission peak or dip. This mechanism makes them highly efficient narrowband or broadband reflectors, as well as transmission filters with applications as laser mirror, advanced detection systems, spectrometers, etc. So, in other direction, you can think of cost efficient fabrication processes and unique appearance have enabled their applications in optical authentication and document security. Their polarization dependent behavior can help them to be used as polarization rotator, wave plates, etc. The control of the optical near field has found widespread application in biological refractive index sensing, fluorescence sensing, nonlinear effects, optical switching, etc., as well as enhancement of the solar light harvesting. So, in the next lecture we will discuss some of these devices based on this effect. So, with that we conclude. Thank you for your attention. In the next lecture we will consider and discuss the applications of matter surfaces and this GMR based devices. If you have got any queries, you can drop an email to this email address mentioning MOOC in the subject line. Thank you.